In the next section, let's see some first simple examples of approximation algorithms. These don't use a lot of fancy knowledge about the problems. They're more to get us started. But they're also, in a way, best possible. Recall our good old friend Vertex cover. So we have a graph and a subset of vertices so that every edge has an endpoint in the chosen set of vertices. That's a vertex cover. In formal language, you can write it like this. If edges are two-element subsets, we certainly want the smallest such, because taking all vertices always is a valid vertex cover. But how, if we're given some set C, how can we prove that that is optimal or close to optimal? Right, so you can easily check that it is a vertex cover. Amazing. You can try to solve this, we know, NP-complete problem to find the smallest vertex cover. That's not going to be practical. So we need some other way. Stay. We can't really modify the specific solution we got. So all we can do is try to get a lower bound on the optimal value. Then we can compare against that. How to do that is problem specific. Here we can do something simple. We can look at matchings. A matching in a graph is just a subset of the edges, so that if you take the same vertices and just this subset of edges, the resulting graph has degree at most 1. Or you can say it in many other things. You can say the edges form pairs of vertices, or the connected components have at most 2 vertices in them. Let's maybe do an example, right? So this is a matching. There could be isolated vertices lying around. And there could be some underlying graph that I'm not drawing, but this is a matching. What you can't have in a matching is further connections. So that's an easy definition. We'll look at different types of matchings. So just be sure to keep them separate. There's maximal matchings, or I like to call them inclusion maximal to make it a bit more explicit what we mean. This is a matching where I cannot add any further edge from the graph without destroying the fact that it is a matching. This could or could not be a large set. It just means you cannot add anything to the set. Then a maximum matching is one of maximal cardinality. So just the two terms. I'll try to use inclusion maximal and maximum to keep it separate. And finally, a perfect matching is just one where we have as many edges as we could possibly have in a graph of v and vertices. So all the vertices are paired. Perfect matching means everyone has a partner. And the perfect matching certainly is maximum, because you cannot add anything. And every maximum matching, of course, is maximal, but the converse is not true. So the good thing about maximal matchings is that they're very easy to find. If you're given a graph, you can just at random pick an edge, add it to your matching, as long as it doesn't connect anything that already has an edge, and you keep going. And if you can't add any of the edges in the graph, well, then you're maximal by definition. So very easy to find. Maximum is a lot harder conceptually. It's complexity-wise still polynomial time, even on general graphs. But on general graphs, the algorithms are somewhat intricate. So it runs in polynomial time, but not linear time. And the algorithm is a bit tricky. It's Edmonds' algorithm, or the Blossom algorithm, if you want to look into that. We won't use it, or we won't use it beyond the fact that there's a polytime algorithm. So why am I talking about matchings and vertex cover? Well, simple observation. If you have any matching and any vertex cover, the vertex cover is going to be at least as big as the matching. Why is that the case? Simple proof. Okay, there's this weird bug why the things jump around. Take any edge in the matching. See, the vertex cover has to contain either of the endpoints, or maybe both, but certainly one of them. And also, all the matching edges are disjoint as sets. So if I'm trying to cover all edges in the graph, I have to cover all the matching edges. And for the endpoints, I know that they're in the matching edges, they're only usable for covering one matching edge. So I need to pick one endpoint per matching edge in any vertex cover. So C must have at least as many vertices as M has edges. Okay, simple. Again, little picture. If this is your matching, even if it's not maximal, there could be many vertices that maybe have some connections in the underlying graph. Let me draw the underlying graph as well. I don't know if you can see any difference. So let's say the matching is the red thing. Then to cover the red edges, you have to pick one of the endpoints, but because they're disjoint, you have to pick one each to do a vertex cover. There's no way around it. Okay, that's an easy observation, but it means we can get a simple approximation algorithm for vertex cover as follows. Find an arbitrary maximal matching. We can do that with this greedy algorithm that I just sketched before. Here it's spelled out. You start with the empty set, you go through the edges in some arbitrary order and try to add each. And if that is no longer a matching, then you discard the edge, but if it is, you keep it. Now what's the output? You take for every matching edge both endpoints into your vertex cover. And that's going to be a 2 approximation for vertex cover. Why? Well, 2 things we have to show, right? One, the output is indeed a vertex cover, so we call this C. Suppose some edge was left uncovered. So there's an edge here that I'm not covering, but I took from all the matching edges both endpoints. So they might lie somewhere here, but I didn't take either of those 2 endpoints. Well, then I could have added this edge to the matching without violating that it is a matching, and that's a contradiction to how we pick things. So it has to be a vertex cover. And second, the fact that it's a 2 approximation follows from this lemma. Every possible vertex cover has to be at least as big as our specific matching, even if that's not a maximal one. And so we only do twice as bad by picking both endpoints. So our C is 2 times this, and we know that opt has to be at least M. So you could puzzle together what C divided opt is by using here we have exactly, sorry, here is an equal, so it's 2M, and for op we use the upper bound, so we get 2. Okay, that's a very easy approximation algorithm. And as a first example, maybe that's all we do. Now, it feels like you should be able to do better than this very simple algorithm. Maybe all we need is a closer analysis of this specific algorithm. But it turns out that's not the case. And an interesting tight example is the complete bipartite graph, where you have all edges between the left and right points. So everything is connected, but there's no edges between the red and the green side. Bipartite means you can split the vertices into two sets so that there's only edges between the sets, not within the sets. A maximal matching could be this one. And because it's a complete graph, everything's symmetric, you can always pair up vertices somehow. You can always find a perfect matching in this graph. So that will be M, and you'll output all vertices in your greedy algorithm. But of course, you could have just picked all the red vertices, and they have to cover all the edges because there can't be edges between the green vertices alone. For example, this would have been enough. So here, any algorithm that starts with matchings will end up with this factor 2. And with a bit of an extra assumption, without getting into what that is, there's a conjecture. If you assume that that conjecture is true, then people have proven conditional on that. There's no constant factor you can improve upon this 2. You can do a 2 minus some function of the input size approximation. But if you want epsilon greater 0 and a constant, that's unlikely to exist for vertex cover, which is somehow striking that this very simple algorithm that we just proved correct on one slide is the best you could hope for in the worst case. It's a bit disappointing maybe, but that's what the worst case looks like.